Fields Institute, founded about 25 years ago, and it is a think tank for everything mathematical. It is a unique place mandated to foster collaboration, education, and innovation in mathematics and the many industries and fields that mathematics supports. And tonight, we celebrate mathematics by listening to some of the leading exponents of the subject. In particular, we honor 2014 medalist Artur Avila as he takes us through some insightful ideas about the mathematical study of chaos. But we also celebrate Canada and its unique contribution to the global mathematical enterprise. Distinguished guests, dear colleagues, old friends and new friends, good evening and a very warm welcome. My name is Kumar Murthy. I'm the director of the Fields Institute for Research in Mathematical Sciences. And on behalf of the Institute, I thank you for joining us at the public opening of the 2019 Fields Medal Symposium. If you had to venture a guess of what you might be doing on a wonderful autumn evening like tonight, listening to talks about math might not be the first thing you would guess. And yet, here we all are. Math seems to spark a unique fascination, maybe in some even a love-hate relationship. We may not be able to explain it or understand it, but the fascination is real. And that applies to professionals and amateurs alike. The great naturalist Charles Darwin felt that through math one acquired an extra sense. And perhaps we all aspire to that extrasensory perception. And tonight, we celebrate mathematics by listening to some of the leading exponents of the subject. In particular, we honor 2014 Fields medalist Artur Avila as he takes us through some insightful ideas about the mathematical study of chaos. But we also celebrate Canada and its unique contribution to the global mathematical enterprise. John Charles Fields, after whom the Fields Medal is named, is from Hamilton. And for many years, he was a professor at the University of Toronto. In the wake of the First World War, he wished to conceive a prize to help to foster cooperation amongst all nations. Moreover, the medal was meant to recognize not just a specific achievement, but the promise of even greater achievements. The medal is normally awarded to researchers who are under 40 at the time that they receive the honor. In terms of the positive and constructive role that Canada has played, is playing, and will continue to play in global affairs, I venture to say that Fields' desire of promoting international cooperation and of having faith in young people to build a greater future are typically Canadian approaches to the world. Besides the medal, the Fields Institute is also named after Professor Fields. The Institute was founded about 25 years ago, a little bit over 25 years ago, and it is a think tank for everything mathematical. It is a unique place mandated to foster collaboration, education, and innovation in mathematics and the many industries and fields that mathematics supports. Every year, the Institute hosts over 150 workshops, conferences, seminar series, outreach activities, and special lectures. And last year alone, it drew over 9,000 participants from around the world. We are proud to welcome world-class mathematicians and researchers who come to Fields to further their areas of expertise. The work they do at Fields has both local and global impact. The Fields Institute is special in that it pays a delightful disregard to disciplinary boundaries. It supports a wide array of activity in mathematical sciences, from fundamental research to multifarious applications in the sciences, in medicine, in engineering, and a host of other fields. All of this activity would simply not be possible without supporters of all kinds. The Fields Institute receives generous funding from the provincial and federal governments. We are also supported by 9 principal sponsoring universities across Ontario, 16 affiliate universities, private donors, and corporate partners. In addition, I would like to thank the generous donors that make it financially possible to hold the Fields Medal Symposium. I'd like to thank our gold level partners, the Great West Life group of companies, whose support helped launch the Fields Medal Symposium in 2012, and Elsevier Publishing, which joined the symposium in 2016. We also recognize our silver level donor, the late James Stewart, whose influence on the world of mathematical education is without compare. A few words about the distinguished lineup of speakers this evening. First and foremost, of course, is Artur Avila, whose exemplary work has expanded the boundaries of mathematical knowledge in dynamical systems and spectral theory, and has set new signposts for the future. We're also pleased to welcome Alejandro Adam, who has just begun the newest chapter of his remarkable career as the president of the Natural Sciences and Engineering Research Council. We're delighted that Andrea Konk, who won the Fields Medal in 2006, is joining us tonight on behalf of the International Mathematical Union. We will also hear from Marcelo Viana, director of the Institute of Pure and Applied Mathematics in Brazil, who will introduce Artur, who's the focus of our celebrations this week. And we'll also hear from 2 academic leaders at the University of Toronto, Professor Vivek Goel, Vice President, Research and Innovation, and Melanie Woodin, Dean of the Faculty of Arts and Science. As broad and as intense as the activity at Fields may be, I sometimes still hear people refer to the Institute as a well-kept secret. Let's change that. If you like what we're doing, and you believe in what we are capable of doing, I encourage you to share your thoughts and your experience here tonight through whatever medium you are comfortable with. You may tag Fields Institute on Twitter, Facebook, and Instagram, and maybe other things even besides. Once again, I thank you for joining us tonight for what is sure to be a wonderful evening in celebration of mathematics. And now I'd like to introduce our first speaker, Professor Vivek Goel. Professor Goel is a distinguished scholar in public health and currently the Vice President of Research, Innovation, and Strategic Initiatives at the University of Toronto. Please join me in extending a very warm welcome to Professor Vivek Goel.
Thank you, Kumar. Good evening, everyone. It's a pleasure to join you and welcome you all here to Victoria College at the University of Toronto. Before we begin, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. The Fields Institute is one of the world's great centers of expertise and innovation in the mathematical sciences. Fundamental research of the sort that is happening at Fields is extending our knowledge of basic mathematical concepts, and it is stimulating new ways of thinking about how to solve problems in many other fields. Mathematics is a true enabler. From music to art and advanced manufacturing, from statistical analyses of politics, sports, and the economy, to the planning of cities and the development of powerful new drugs, mathematics plays a crucial role in a vast array of disciplines and human activities. Scholars at the Fields are enabling game-changing breakthroughs that are helping us to respond to the significant challenges that confront us locally, nationally, and globally. The University of Toronto is fortunate to have the Fields Institute located on its St. George campus. As Kumar mentioned, U of T's connections to Fields began with the Institute's namesake, who's an alumnus, a professor, and one of the early pillars of the Canadian research community. And the Institute continues to enrich this university's teaching and research activities, as well as those of its partners. It's a wonderful example of what a research institute should be, a place where scholars from around the world can gather to ask questions, explore new pathways, bounce ideas off each other, and engage researchers at other institutions, as well as government, industry, and community partners in their work. We're proud to be associated with the Fields Institute and very pleased to have the opportunity to welcome events such as this. I'm particularly delighted this evening that we have my good friend Alejandro Adam, who's introduced. He's no stranger, I would hope, to the mathematical community, having been the head of a, shall we say, sister institute or a competing institute, one out on the West Coast. But now we're very proud to have him as the new president of the Natural Sciences and Engineering Research Council, and we look forward to continuing to collaborate with NSERC on many great initiatives. It's a great pleasure to be here to welcome the 2014 Fields Medal winner, Professor Artur Avila, and we're looking forward to hearing from him this evening. So I'd just like to conclude by thanking the Fields Institute for its partnership and for making such a profound contribution to putting Toronto and Canada on the world map in mathematics. Thank you very much.
Thank you, Vivek. Next, I would like to invite Professor Melanie Woodin, who's Dean of the Faculty of Arts and Science at the University of Toronto, to share a few thoughts with us. Besides being the Dean, Professor Woodin is an accomplished and highly cited neuroscientist in the Department of Cell and Systems Biology. Professor Woodin.
Thank you, Kumar. I'm delighted to have the opportunity to greet you on this evening on the occasion of the Fields Medal Symposium. As you have heard, the Fields Medal is named after the University of Toronto mathematics professor, John Charles Fields. He was truly a visionary, thinking of themes that are as relevant today as they were when he formulated them almost a century ago. I speak here of the importance of recognizing and nurturing excellence, the importance of international collaboration, and our view as academics and teachers that the future of the world depends on encouraging young people. The Medal Symposium is an excellent affirmation of all of these principles. The Faculty of Arts and Science at the University of Toronto, which I have the privilege of leading, is home to more than 30 different academic departments and many centers, as well as home to 30,000 students. We have leading researchers and teachers in a broad spectrum of fields. And while our efforts are across a broad range of disciplines, collaborations with the fields helps us focus and magnify those efforts as they relate to the mathematical sciences. Sitting next to the Institute, as we do here at the University of Toronto, gives us the opportunity to interact with and benefit from those visitors, not only for our faculty and researchers, but for so many of our graduate and undergraduate students. And we share a deep commitment to training those young minds. The mathematical sciences, including mathematics, computer science, and statistics, are having an enormous impact on many fields. And our world is being truly reinvented through these quantitative models. There's never been a better time to increase our exposure to and interaction with these disciplines. So congratulations to the Field Institute on organizing the symposium and the public lecture, and congratulations to Professor Artur Avila. Thank you.
Thank you, Melanie. The next speaker is Professor Alejandra Adam, who has already been pointed out, is President of the Natural Sciences and Engineering Research Council of Canada. Besides that role, Alejandro is a highly accomplished researcher in the field of mathematics, faculty member at the University of British Columbia, where he has been the Canada Research Chair in Algebraic Topology and Group Cohomology. From 2015, he also served as the CEO and Scientific Director of MITAX, which supports partnerships between universities, companies, and the government to support industrial and social innovation. Alejandro.
Thank you very much for that introduction, and thank you to the previous speakers for their kind words. Well, I'm here before you as a mathematician. I know the great value of the Fields Institute. I first came here as a participant in the program in 1996. I remember spending 3 weeks here in a program in algebraic topology. What else? And leaving that program with my research taken to another level, excited about the area, and several papers came out of that participation in the Fields program. I have also organized 2 conferences here at the Fields Institute. So despite what Vivek said, I'm an equal opportunity user of mathematics institutes in Canada, in fact, around the world. So as president of NSERC, it's a pleasure for me to say that we support the Fields Institute, as well as 5 other mathematical institutes. And I should say mathematical sciences institutes, which include statistics and allied fields. Canada punches above its weight when it comes to mathematics statistics institutes. We can be very proud of that infrastructure which has been constructed around the country. And for what I'm told are limited amounts of money, great accomplishments are achieved. And in particular, the Fields Institute has achieved so much and is an international reference point. Wherever we go around the world, we're told about the great stuff that's going on at the Fields Institute. And the people here and the universities in Ontario, and not just the University of Toronto, but the other universities that also support the Fields Institute, can be very proud of these accomplishments. Now, in particular, today's honoree, Artur Avila, I feel he's a great Fields medalist because he's the first Fields medalist from Latin America. And you may know that Brazil has a very active mathematical community, and a very organized and concerted effort was made by our Brazilian colleagues, and Marcelo Viana might mention this, to develop mathematics in that country. And in particular, IMPA, Marcelo's Institute, and other institutions in Brazil have done a remarkable job. And Canada can learn a lot from what Brazil has done for mathematics. We will hear about the great mathematics that Artur Avila has done in dynamical systems and related subjects. It's one of the key areas of mathematics. Now, mathematics, as we understand it, ranges from the pure to the applied, touches on all the natural sciences, on the social sciences, even on the humanities. It is ubiquitous, and it's a great subject to work in. So I want to congratulate, of course, Artur Avila for his great achievements, the Fields Institute for the remarkable excellence that they support, and the breadth of their accomplishments and their outreach to the communities. And hope that you'll all stay and enjoy the mathematical lecture. Thank you very much.
Thank you, Alejandro. Actually, the 2014 medals had a lot of firsts. As Alejandro mentioned, Artur was the first winner from Brazil. Manjul Bhargava was the first winner from Canada, India. And Miriam Mitsakani was the first winner from Iran and also the first female recipient of the Fields Medal. So there were a lot of firsts in 2014. Next, I'd like to introduce, I ask Professor Andrea Konk to share a few thoughts with us. Professor Konk is representing the International Mathematical Union, but he is himself a Fields Medalist in 2006. He was awarded the medal for his contributions to bridging probability, representation theory, and algebraic geometry. He's currently a professor at Columbia University, and he's on the executive committee of the International Mathematical Union. Andre.
Thank you, Kumar. Thanks, everyone. Good evening. I'm here representing the International Mathematical Union. It is the International Mathematical Union that awards the Fields Medals in recognition of outstanding mathematical achievements by the laureates. So they need to celebrate both the incredible heights that modern math has reached and the genius of the people who took us there. I think that need is particularly acute today. And the reason it's acute is because math and science in general are under constant, I should say, attack by people who want to take the truth and the depth to not make them not absolute concepts, but rather concepts that are relative and optional and pliable and otherwise political. And I want to thank all of you here today who came to celebrate and support the true truth and the true depth of mathematics, and so I want to thank you for that, as well as I want to thank the Fields Institute and all the organizations that support the Fields Institute, and representatives of the University of Toronto, the provincial government, and every individual who makes a contribution toward the success of this event. Thank you.
Thank you, Andre. Now we move to the next phase of the program. Our next speaker is Professor Marcelo Viana of the Institute of Pure and Applied Mathematics in Brazil. Professor Viana is an award-winning mathematician who works in dynamical systems theory. He was vice president of the International Mathematical Union from 2011 to 2014. And he's the director of Brazil's institute, IMPA, which roughly is the Institute of Pure and Applied Mathematics. He will speak on renormalization, the work of Artur Avila.
Oh, okay, I found it. Good evening, everyone. It's really an enormous honor and privilege to be able to be here with you today and speak about my friend and colleague Artur Avila and his contributions to mathematics. I want to start by giving you the summary of the things I want to talk about. Artur is an outstanding mathematician. He is not only someone who's extremely powerful in technical terms, he's a dynamicist, meaning someone who does dynamical systems, and I will try to define quickly what that means. But is also someone with really superpowers of analysis, of mathematical analysis. And something that I find even more fascinating is his capacity for building strategic plans for attacking and solving very difficult problems. In mathematics, as in life, you have to plan ahead and set goals and try to build bridges in between successive goals, and Artur is particularly skillful at guessing where the base points for those bridges should be and believing that they are feasible and making them happen. Now, unfortunately for me, he has done too much in mathematics. His contributions cover several different fields, and it would be absolutely impossible for me to try to survey them here. They cannot possibly be summarized in a lecture like this one. But there is some unifying principle behind not all of what Artur has done, but a lot of his main contributions, and that's the idea of renormalization. I will speak a little bit about that later on, but renormalization is something that physicists discovered. They realized that certain critical phenomena, their laws, their rules are essentially not affected when you rescale different quantities that are involved in the formulation of these phenomena. And mathematicians have been extremely successful in using that idea of renormalization to find new theorems, prove new theorems and new ideas. And Artur is absolutely the most skillful of these users of the notion of renormalization. So let me begin by telling you a little bit about the character. Artur was born in Rio in 1979, and when he was 13, he got his first big award, a bronze medal at the Brazilian Math Olympiad. And the reason that is relevant, besides being an achievement, is that IMPA, my institute, runs the Math Olympiads in Brazil. So Artur had to go to IMPA to get his medal, and that's how this secondary school kid learned about the institute. The next 2 years, he got 2 gold medals, and at the Brazilian Math Olympiad. And in 1995, he came here to Toronto to take part in the International Math Olympiad, which is like a FIFA World Cup of Math Olympiads. And he got a gold medal here as well. I'm told that he was expected by his colleagues to join the Brazilian national team next year, in 1996, and he refused to do that because, well, 2 reasons. He already had a gold medal, why look for another one? And secondly, because at that point he had enrolled for graduate school at the Institute. So he stayed with us from 1995 to 2001. And in 2001, he completed both his master's and his PhD. His thesis advisor was my late colleague, Wellington de Mello, who was shown there on that photograph, sailing near Rio. So that closes one cycle in Artur's life as a student. And then he started becoming a grown-up mathematician. From 2001 to 2003, he went to Paris, to Collège de France, where he was a postdoc with Jean-Christophe Yocoz, himself a former Fields medalist. And then he was hired by the French National Research Council, CNRS, first in a junior position, chargé de recherche, and then in 2009 as directeur de recherche, which is their senior position. And as you can guess with a quick calculation, he was 30 years old at the time. And that's extremely unusual. Some of my French colleagues were wondering whether that was the first case of someone becoming directeur de recherche at the age of 30. That's extremely unusual. That's a promotion that they get much later. From 2006 to 2009, he was a Clay Research Fellow, and he started this period by going back to IMPA, where we made him an offer, and he became, he took from then on until today a special position with us. And since last year, I think it's last year, he is a professor also at the University of Zurich. So that's his professional trajectory. And before I talk about his work, I want to point out one very special characteristic of Artur's. Mathematicians come in all sorts of flavors. Some of us like to collaborate, others like to work alone. Artur is on a class of his own. He has about 80 papers, and he has about 50 collaborators, and that's absolutely fantastic. It says a lot about his capacity for interacting with other colleagues. Some of them are here today. Some are senior, some are quite young, and in that way is also playing a role in the development of extremely brilliant young mathematicians that are following his lead. The bulk of his work is in dynamical systems and ergodic theory, and I'm going to try to explain a little bit very quickly what that is, what part of mathematics that is. But he also has, if you read the keywords there, works in global analysis, operator theory, quantum theory, statistical mechanics, structure of matter, combinatorics. All that says a lot about the diversity of the mathematics done by Artur Avila. So what is dynamical systems? We are concerned with modeling the way phenomena, natural phenomena, artificial phenomena evolve in time. And if you want to express that, the first thing you need is a space to represent the possible states of your phenomenon. And that's what I try to describe here with this line. The points in this space M represent different states of the phenomenon that you want to analyze. Example, if you happen to be interested in the pendulum of that old clock you have at home that keeps doing this, the state is described by two things. One is an angle expressing what is the position of the pendulum at that particular moment. And the other data that you have to provide to describe the state of the pendulum is the velocity with which it is moving. So in that case, x, these points here, each point in this space represents the state, and in the case of the pendulum, x will be formed by one angle and one number, this number representing velocity. And then the second thing you have to describe the evolution of the phenomenon is the law of evolution. In the case of the pendulum, that would be a differential equation. But I'm going to stick to a simpler model where the system evolves by iterating a transformation. There's a transformation that takes the present state of the system and calculates what the state will be within after 1 unit of time, whatever the unit you choose to use. So this, you go from state x to state f of x in 1 unit of time. And then 1 unit of time later, you are in the new state that is represented as f2 of x, that is obtained just by applying this transformation again, and again, and again. And your ultimate goal is to describe what this sequence of successive states behaves like. What is the behavior of the sequence if you keep on iterating forever? Where is this phenomenon going to evolve to? Now, we also learn quite quickly when we do dynamical systems that we cannot expect to answer that sort of questions for every transformation, for every state x. So we have to focus on typical values of the initial state and typical laws of evolution. And this will be a constant in everything I'm going to say. Now, let's give one example. It's perhaps, well, certainly the simplest, interesting example that we can have. Your transformation is given by a function. This is the graph of the function. These are called unimodal maps for the simple reason that there's one maximum, that's the mode, and it is unique. And so in this case, you would start with some initial state x here, and you can calculate the next state f of x just by taking the vertical line from the point x until it meets the graph, and then that gives you f of x. And the way you iterate is by now starting with f of x, going vertically until you meet the graph again, and that gives you f2 of x, and so on. In this case, you get a sequence that is going to the right, but at the next time, that's no longer the case. And this sequence can behave in rather complicated ways. So when I was starting graduate school, we would draw these pictures, and there were ideas, but the feeling I had as a student was that this was completely hopeless, that we would never be able to say interesting things about the sort of behavior that you get when you do these iterations. And 30 years later, essentially we know everything we could hope for, we could hope to know. And that was the work of a whole generation of our best mathematicians, with Artur as one of the highlights. So let me tell you one theorem. Again, the purpose is to know how this sequence behaves and when you iterate. Let me state here one theorem that is a combination of works Artur has done with Misha Ljubic, who's here today, and also with Carlos Gustavo Moreira, who's our colleague at IMPA, and with Artur's thesis advisor, Wellington de Mello. So you don't have to read the words. I'm going to tell you what this theorem means. It means that if you focus on typical, then there are only two things that can happen. Other points and other transformations might behave in different ways, but if you focus on typical behaviors, there are only two possibilities, and they are called regular behavior and stochastic behavior. Okay? In order to give a sense to this, I have to explain what we mean by regular and by stochastic. Now, regular is easy. Regular is exemplified in this picture, is the situation when you start iterating, and after a while, you realize that what your sequence is doing is jumping between two different points, just doing this repeatedly, or three different points, or four different points. And we call that a cycle, an attracting cycle. And to have regular behavior is just that what happens to the sequence is this not very exciting thing, that it starts repeating itself. Okay, and that's this picture here. Now, life is more interesting than that. There's an alternative that is stochastic behavior, and which means, to begin with, that the behavior of the sequence is a lot more complicated. It's sort of chaotic. Looks like it's not following any special rule, and yet it is. And I'm avoiding the technical formulation. What stochastic means is that the behavior of this sequence looks very complicated, but in fact, it follows a very precise statistical rule. You don't know where any individual point fn of x is, but you know how the sequence is distributed in the space in terms of percentage. You know which percentage of time it spends on each different region of the space. This is like if you were trying to find out how the stock market is going to evolve, and you ask me because I'm a mathematician, and mathematicians are supposed to have extra senses and do miracles, and instead of telling you exactly the values of the stocks, I would tell you the probability that they would be within a certain range. That's not as good as knowing the exact values of the stocks, but then again, with that information you could go a long way. So that's what stochastic means here. So you see, if you just focus on typical behavior, there are actually two possibilities only. And proving this theorem was really the climax of a long series of mathematical results. And it's worthwhile quoting here something that Misha Ljubic wrote in 2012. Artur won a prize at the University of Maryland, and Misha wrote an article that starts with these sentences, approximately. The field of one-dimensional dynamics, real or complex, emerged from obscurity in the 1970s and has been extensively studied since. By now, meaning about 40 years later, we have reached a full probabilistic understanding of real analytic unimodal dynamics, and Artur Avila has been the key player in the final stage of the story. So this, I think Misha expressed it better than I could, tells you of the importance that the added value that Artur brought to this field, which was populated by mathematicians of the magnitude of Misha himself, Dennis Sullivan, and many others, Kurt McMullen, and many others. So these are photos with some of the characters. Misha is here, working with Artur. The other co-authors of Artur are here. Wellington de Mello, his thesis advisor, Carlos Gustavo Moreira, joined with Jean-Christophe Yocos, Jacob Pallis, and Enrique Puig also were also at IMPA at the time. So I'm moving to a different subject now, billiards. Of course, everyone knows the concept of billiards, but mathematicians play with slightly different billiards. They were invented initially by mathematical physicists as a model to try to understand the motion of molecules of a gas. Problem with gases is that they are formed by small particles, the molecules, that are in themselves not so complicated, but it's the sheer number of molecules that you have that makes gases complicated, and these molecules keep hitting themselves. And you want to understand this sort of phenomenon of a system. And what was realized was that could be modeled, could be represented in the form of a billiard. I'm sort of cheating here because I'm drawing on the picture a very familiar kind of billiard table, just a rectangle. For modeling a gas, you need to work with tables that have various shapes, and even worse, very high dimensions. This is a 2D table, and for the purpose of modeling gases, you would need a table in higher dimensions, but let's play the game anyway. So on this table, you have a little ball. Just think of this as a pointwise ball, and the ball moves, and eventually it moves in a straight line with constant velocity, but eventually it hits the boundary of the table. And then it reflects elastically, which means that it takes a different direction, following the rule that the angle of incidence and the angle of reflection should be the same. And then there's this segment of trajectory where the ball is still in a straight line. Yeah, I know, the picture is not perfect. I know that. But the angles are supposed to be equal, okay? It's the fault of the artist, not the mathematician. So there's another segment, the ball eventually hits another side of the table, and this goes on like this every time, hitting with this law of the angles and so on. And what you want to do is, again, to understand how this line behaves, especially as time goes to infinity. What happens here? Now, as I said, in the general theory of billiards has to deal with tables with any possible shape and in higher dimensions. But for the purpose of this presentation, I will stick to two-dimensional tables, and I'm going to restrict the setting even further. I'm assuming that the tables are polygons, so they are bounded by a finite number of straight-line segments, and even more, that the angles, for example, this angle here, this here, all the angles are rational multiples of pi. Pi over 3, 2/5 of pi, 3/7 of pi. So a fraction multiplied by pi. So this is the assumption. This is, of course, a very special kind of billiard tables, but one that is extremely rich and for which the theory has been, it is important for various reasons, not necessarily related with gases, and it's an extremely rich theory. So as before you start with a particle, it hits the wall of the table, is reflected, and then there's a magnificent idea, extremely simple idea, that helps a lot in understanding, in answering the question of how these trajectories of billiard balls behave. And I'm going to try to explain the idea with the picture. When the ball hits the wall and comes this way, you can pretend it doesn't. You just take a copy of a symmetric, or the reflection copy of the table, and you let the ball go straight. So here is the little magic idea. When light hits a mirror and comes back, it's as if it went straight across the mirror to the other side. The law of reflection means precisely this. This is the starting point for a construction. Actually, this was explained much better a year ago by Amy Wilkinson here at the Field Symposium. Each successive reflection can be thought of as if the ball was just going straight to the other side of the mirror, to the other side of the reflection wall. Now, using this idea, I'm not going to get into technical details, but using this idea, one can transform the billiard problem into something that looks much simpler, and that's called interval exchanges. Interval exchanges are a very peculiar, very particular type of functions where you have your domain, you break it into a certain number of intervals, A, B, C, and D, and the transformation you do is that you just reshuffle these intervals. So in this case, A, which is here at the left, is mapped to that interval. So the graph of the function is given by this line segment, and similarly with the other segments. So what I'm saying is any polygonal billiard whose angles are rational, by the way, the assumption that the angles are rational is to make sure that this reflection operation only goes on for a certain finite number of steps, and then eventually you stop. You don't have to go forever duplicating these tables. So every billiard can be understood mathematically by understanding this kind of function that we learned to draw their graphs early in school. These are called interval exchanges because the dynamics consists of taking these sub-intervals and reshuffling them. Okay, so here is another theorem that was proven by Artur and Giovanni Forni, who's also here today. They proved, again, the idea is prove things for typical points, typical laws of evolution. And what they did was to prove that for almost all interval exchanges are weak mixing. Now, weak mixing is a technical term. It means the formula that is written there, which I'm sure my fellow mathematicians appreciate, but you don't have to read it. Weak mixing is one of many ways mathematicians express that the dynamical system they are dealing with behaves in a chaotic fashion. So typical billiards are such that because of these successive reflections, after a while, in some sense, the behavior of the trajectory has become unpredictable. Okay, that's one way of expressing that. We don't like, when we say chaos, unlike philosophers who think of chaos as something that has no rules. When we say that, it means it's complicated, but we know how it goes. We can say things about them. That's chaos in mathematics in dynamical systems is always something nuanced. Okay, so here are some of the characters. Artur, together with Giovanni, Misha, again, Misha Lubitsch, and another of Artur's favorite co-authors, Raphaël Cricoyan. Okay, I'm going to now talk about a third subject, and I hope that by now you are kind of feeling that they have apparently nothing to do with each other. One thing is about iterating functions that look like parabolas, the other one is about playing billiards. This one is also motivated by physics. It's called localization. This was an observation made by physics Nobel Prize winner Philip Anderson around 1958. He observed that certain materials that should be electricity conductors quite often behave as insulators due to the presence of either defects or impurities. And that is illustrated in that little video. Upstairs, we have a situation where the particles of the material, think of a metal, okay? Metals are usually conductors. And if their atoms are placed regularly, and that's what these little parabolas all aligned together and similar represent, if that is the case, then electrons are free to move along the material. In quantum mechanics terms, we say that the wave function for the electron is extended. It's represented by that wiggling red line there. The wave function is everywhere, which means that the electron is allowed to go wherever it pleases. Now, if you introduce some kind of defect in the material or impurities that make that these metal atoms are no longer so perfectly aligned and so perfectly organized, then that causes, that's what Anderson suggested, that causes the wave function to get a completely different shape, which is, I try to represent like that. That shape means that the electron is stuck near the center. And physicists call that spatial localization. The wave function for the electron gets to be much stronger in one region than the others, and that, according to quantum mechanics principles, means that the electron is trapped. And that's why there's no electricity transmission, conduction. Now, this is that embarrassing moment where the mathematician is forced to, in order to continue, to write a few formulas on the screen. But I promise this will be very quick and basically painless, so please bear with me. Only a couple of slides. Now, how does one analyze this? How does one analyze, I'm not talking not only mathematicians or physicists, how does one address this kind of phenomenon? Anything quantum is ruled by the Schrodinger equation. By the way, you don't have to understand what is written here. These are just objects that I have to introduce in my speech, and so I take the occasion to introduce them to you. The Schrodinger equation involves an operation H, a mathematical operation. The formula is here if you care to look at it. It's not so important. That is called the Schrodinger operator. And basically, the Schrodinger operator associated to your phenomenon describes nature, describes how this phenomenon is and evolves. A part of the Schrodinger operator that's denoted as V, that's called the potential, and that's where the physics of the material appears. Essentially, if this potential is very regular, that corresponds to the first part of my little video. And if it is a little bit more complicated, that's how we introduce the impurities and the defects into a picture. And this is the most popular choice of a potential. Again, you don't have to care about the form. It's just that I want to be precise about what we are talking about. Now, the Schrodinger operator, associated to it, there are two objects. One thing is called a spectrum. It's a set. And the other one is called spectral measure, and it's a measure. This is not important. What is important is that mathematicians, by looking at these objects, they can characterize the behavior of the electron in terms of these objects. And that's what's written here. If the spectral measure is absolutely continuous, whatever that means, that means physically that the electron is free to move around. If the spectral measure is pure point, again, you don't have to care about that, that means that the spectrum has a localized wave function, and so this corresponds to localization. So Anderson localization, this idea that because of the impurities and so on, the electron gets stuck, can be expressed mathematically in terms of these objects. And if you want to prove and explain and justify Anderson's theory, Anderson's explanation, then this is what you should look at. These are the mathematical objects you should look at. So I promised 2 slides, and I'm fulfilling my promise. No more formulas. This is a picture. It's called the Hofstadter butterfly. It's, I hope you agree, a very beautiful picture. And it is related to what I just said. More specifically, it is related to the spectrum. If you pick here a coordinate alpha, and you cut the picture vertically across this coordinate alpha, what you get, this slice, is the spectrum for the Schrodinger operator for that frequency alpha. So whatever your feelings are about the Hofstadter butterfly, I'm sure you agree it's beautiful, and I'm even more sure that you agree it's complicated, right? So this sort of numerical simulations suggested that the spectrum of this Schrodinger operator is probably a very complicated, very fractal kind of set. And this was formulated as a conjecture. It was conjectured that the spectrum of the Schrodinger operator is a Cantor set. The Cantor set is the most basic of all the fractals, and this was a conjecture for quite some time. Around 1981, mathematician Mark Katz offered 10 martinis for whoever solved this problem. I think it is generally understood that this meant that he thought it was a very difficult problem. And it became known as the 10 martini conjecture, and it was solved by Artur and Svetlana Zhytomyskaya, who's also here today. They proved that indeed the spectrum is a Cantor set, is this type of fractal set for all, essentially all potentials and all irrational frequencies. And at around the same time, Artur, Svetlana, and David Damanik proved that the spectral measure is absolutely continuous. So if this parameter is small, if parameter lambda is less than 1. So for small parameters, there's no localization. That's what this theorem says. The electron is free to move around. And I was fortunate to find a picture on the internet where Artur, Svetlana, and David stand for posterity. Even more, perhaps just as impressive for me at the time, was that around 2014, when Artur was getting the Fields Medal, he was working on something that I think no one in the field thought it was possible. And let me try to explain this. Theoretical physicists, when they deal with this problem, had a tendency to think in terms of two completely different theories that they call small potentials or large potentials. And in terms of these variables, that means small lambda much smaller than 1, or lambda much larger than 1. And I think there were even two different tribes, one working in small potentials and the other one in large potentials. At least people specialize on one of the sides of the theory or the other, because they looked apparently very simple. And then around 2013-14, Artur decided to set his eyes on an ambitious goal, which was to build a theory, a global theory, that connects those types of behaviors, those two types of behaviors. It was eventually published in 2015. And this theory is, to the extent that I understand it, mostly from explanations that Artur gave me, is surprisingly precise, surprisingly elegant, simple, the way he managed to connect these two sorts of behaviors that were thought to be quite different. Okay, unimodal maps, billiards, and now quantum mechanics, Anderson localization. What do these things have in common? Well, they actually deal with very different situations, but one thing they have in common is the way Artur and his collaborators approached the problem, and that was using this idea of renormalization. So I promised I would say a few words about what renormalization is for physicists. Let me do that. For example, there's a thing in physics called phase transitions, which is when substances change phase status. For example, think of water freezing into ice. That's something that we observe, especially in Canada, quite frequently, not so much in Brazil. But it's extremely complicated phenomenon from the physics point of view. Water that freezes, it's something extremely complicated. There's one temperature. As the temperature decreases, it's really hard to understand, to describe. And what physicists discovered was this following trick. If instead of looking at this temperature, you look at the temperature that's much closer to the freezing point, then you get the same law. The temperature is different. So something changed dramatically. But you get the same law if, as a compensation for rescaling the temperature, you rescale space. You approach the critical temperature, the freezing point, but if in your equations you rescale distances suitably, then you get essentially the same law, essentially the same description of the phenomenon. And the reason this is interesting is that it gives you a way to probe the phenomenon very close to the critical temperature, the freezing point, which is very useful, at the relatively mild price of working with distances that are bigger. And that's not a big deal. So that's one. Renormalization in physics means a lot of different things. But they somehow share this idea that different quantities, if different quantities are rescaled appropriately, you get the same, essentially the same law. So mathematicians apply that in the way that I'm going to describe to you. So let's start with a transformation F, my dynamical system. And now I'm going to think of this dynamical system as a point in the space of all dynamical systems. So this little dot there represents, in this space of all transformations of all dynamical systems, represents that law of evolution. I choose a domain, a small domain in the space where this transformation takes place, so a certain subset of possible states. And for each point in this set, I just iterate it, I let it evolve until it comes back. So
So G represents the, we call that the first return map. The map that picks that little blue dot and brings it back to the blue domain. That's a new map, which you can view also as a dynamical system, a new dynamical system. And renormalization means going from the initial dynamical system to this one. What did we achieve in doing this? We now have a dynamical system that is defined on a smaller domain. So we rescaled space, we zoomed in space, at the expense of taking more iterates to come back. So we zoom in space, and we slow down time. Instead, what used to be several iterates now is a single iterate for this. And the expectation is that the combination of these two things, rescaling space by zooming in and slowing down time, will be a probe into understanding the local behavior of your dynamical system in much the same way as physicists use renormalization, for example, in thermodynamics. So one concrete, slightly more concrete example. Let's go back to Unimodal Maps. Iterate a second time. This is one of those maps that I showed you. Iterate a second time, you get a graph like this. And if you're lucky, the graph will have this feature that you can draw a little square. And there's a graph, a smaller graph inside this little square. Okay? So this is the blue thing that I did before, looking into a smaller domain. Just cut out that square. So you have this. This is, but you see, this takes 2 times to iterate. So, and then you just take this part, forget about the rest, take this part, rescale it, make it big, make it go back to size 1, and in order to have to make it more elegant, you also flip it so that the this point, instead of being a minimum, becomes a maximum. So this is the simplest, the first kind of renormalization that was used in dynamical systems. It's the period doubling renormalization, and that's one of the tools, basic fundamental idea that was used for this progress that Misha Ljubich mentioned in the quote that I made, and that is also behind the proof of his theorem with Artur. And it's a different kind of renormalization that is used for studying billiards and interval exchanges, and yet a different kind of renormalization that is used for studying Anderson localization, the behavior of Schrodinger operators. Each time it's a different thing, but there's a common thread, a core idea, this idea of rescaling space, rescaling time to compensate, and in this way getting a sort of mathematical microscope to look into your system in big detail. Okay. I want to finish by showing you a few pictures and saying perhaps a little more about Artur. So this is this picture became hugely famous in Brazil 5 years ago. That's the image of him getting the Fields Medal from the president of South Korea. I am particularly fond of this one. This is a sort of 5 generations of mathematicians together. This was taken on the roof of Impus building. So it starts with Artur's academic great-grandfather, Stephen Smale, Fields Medalist in 1966. Jacob Pallis was Smale's student. Wellington de Mello was Pallis' student, and then Artur did his thesis with Wellington. And they are joined by my late colleague Mauricio Peixoto, who was, I think, 95 or 96 at the time. He was the last remaining founder of our institute. Now, these photos also became quite popular in Brazil, especially this one made it the cover of our best monthly magazine. The journalists wanted to understand how Artur works. What does he do? And he managed to convince them that that's the way he works. That's his office attitude. And the kids love this. I mean, there's this story. I had a student who took a course with me at IMPA. He was a former colleague of Artur's from high school. And then after high school, they split. Artur did math, and his friend did, I think, literature or English or something. And Artur's friend felt that life was too hard at the university. He was having a hard time dealing with learning literature. It was, the cost-benefit of it was really too tough. So based on what he knew of, he changed into mathematics, because clearly it was much easier. Artur had a much easier life. And I'm mentioning this because I know Artur very well. He is one of the most hard-working mathematicians I've ever seen. It really works hard, okay? It doesn't just come by miracle. And yet he has a way of doing it. You see this blackboard on the back, it's all written. But one thing that strikes me with Artur is that he's able to do mathematics just by lying on the bed. It doesn't show. One of his best friends is a movie director, and would dream of shooting a documentary about Artur, but he said it would be completely dull. I mean, just can imagine an hour and a half. So, and the thing is that most of us need to write at least I do, need to write to help with thinking. And Artur kind of doesn't need it. He just is able to think of these little Lego pieces that are mathematical ideas and putting them together and building blocks from them. So yeah, it's very, very boring from the movie point of view. Another aspect that I want to stress here is Artur's pop star status that he has, which makes him dear of our media. I think he does this more out of sense of duty than pleasure, but is quite often interviewed. I don't think you have to know Portuguese to get the general idea of what is written there. This is our main cable news channel, and this was one of several interviews that Artur did that are really important to... I was talking with someone today who said, well, in my country, people are kind of proud of saying that they don't understand mathematics. They were bad in math. I don't think that's the case in Brazil. People will probably be ashamed, but definitely not proud of saying that they were not good in math. And that is to some extent the result of the effort that some of us do to value mathematics, and Artur is absolutely fundamental in that regard. And to finish, I think the most important, from my point of view, the most critical importance of his trajectory, of his very existence, is as a role model for young people. The photograph that you see on the left was taken about a year ago. It's the award ceremony for the Brazilian Math Olympiad. Those are the gold medalists, about 600, 576 to be precise. The Brazilian Math Olympiad involves every year more than 18 million kids. This year we added a couple more. We had 4th and 5th graders, so we are reaching 20 million kids. That's 10% of the population every year taking a math Olympiad. And in 2018, we had a great opportunity. We set the award ceremony at the International Congress of Mathematicians. So these kids, the day before, had watched the award ceremony for the Fields Medal, and then they came back the next day to get their own gold medals for the Math Olympiad in the same venue. and they are just standing for the national anthem as they were taking a photograph. And Artur was decorated during that ceremony, and the other photo is of him giving a speech for the kids. And ultimately, that's what, at least that's one of our French colleagues who were at the Congress, International Congress of Mathematicians, wrote afterwards that the whole thing would be completely senseless. The whole thing, meaning the Congress, the Fields Medals, and all that, would be completely senseless, except for one detail: the kids. The opportunity to tell the next generations that the things we were talking about, that mathematics is important, and it's important for all sorts of reasons. And that's a message that we have to keep repeating and repeating and repeating. And I'm not going to repeat it anymore. Thank you very much for your attention.
It's on? Yeah. So I'm very happy to be here with this opportunity to give this presentation. Thank you, Marcelo, for the wonderful work. So they can see that I could only dream to be able to organize such nice slides. And on top of that, it shows the danger of doing kind of slides for me and of not communicating with the person that's presenting you, because we are going to have some repetition. But maybe since sometimes you don't get things in the first time, and actually my talk will be simpler than the one given by Marcelo mathematically. Maybe even if I repeat, maybe it will be useful for some. Okay, so I'll be less technical. I think I have essentially one very simple formulas, no equations are really in our setup, but we have very similar pictures in the beginning. What I want to say is how we could start to be interested in this field, and how what I'm trying to explain what you're trying to achieve. And I started with something related to one of my first papers, the one with Ljubich and with Wellington. There is in the first page, we start with a story talking about the connection to biology. So I start with this as motivation. So how does dynamical system appears? You could imagine that you try to model an evolution of some population of whatever, a bacteria maybe. And bacteria, you check the population, let's say now, and then you check again in 10 minutes, depends on the unit of time that makes sense. And you find out that bacteria tend to maybe spread, and they reproduce, and then maybe you have X bacteria at initial moment, and next moment you have lambda X bacteria with some value of lambda. And typically, badly for you, lambda is a number bigger than 1. And this means that you get more bacteria and more and more and more, and then you get to what you see as exponential growth. You have each time more bacteria, and you get an infection and so on. So that you might be interested in this. And then you realize that it is maybe too simple model. Of course, you may kind of keep getting more bacteria initially, but eventually it has to stop because maybe it will kill you, and there's no more space for the bacteria. So actually the problem is that if you have too much of the population of something, they start to inhibit each other. So you get overpopulation, and maybe now they try to die off. There's no space, there's no food, they're bad. So in a sense, it's too simplistic, the initial model that just had some kind of multiplier. So you need to correct. And so you try to make the simplest possible correction, and you get the picture done that Marcelo showed already, which is something like this. So you do the simplest possible correction, which involves adding, so you have just originally x goes to lambda x, and you add a quadratic term. So here I wrote as x goes to r, so there is a parameter r. I don't know what's r. R is 2.7 in this case, but it may change, like the lambda there. And there is x times 1 minus x. This gives a quadratic term, and you get this kind of law, I drew a diagonal for reasons that were already shown by Marcelo that showed that when you start to iterate maps, if you want to see graphically what happens, you do kind of collisions with the diagonal. I don't need to explain, thanks to him. But basically, that's the graph. That's the simplest modification that we could do to the simple model. And as Marcelo said, what you're interested in kind of repeating the rule. So it tells the rule what you do after one step of time, and then it keeps going. There is a green point, because that's a special point that if you are at that, it doesn't change next time. So that's a kind of exactly get the same thing, is an equilibrium point. And what happens that, well, what if you're not at equilibrium, you start maybe here or whatever. You are going to do something else. Like you started something that was started downstairs, it hit there, then as Marcelo does, we do this game, and you keep going. It turns out that our equilibrium was some stable equilibrium, so if you started somewhere else, it tends to go to it. And then your evolution, so you imagine that your population of bacteria actually goes to some limiting behavior, which then doesn't look like it's changed. It has stabilized after some time, and it hits stabilization independently of more or less where you started. So you don't need to have started the kind of already at equilibrium to kind of eventually kind of settle off at that. So that's this, and this happened like I just took some a specific example like this 2.7 as an example. Well, it doesn't kind of end like this. You could have to have another parameter like the lambda. Does it change like for when you had this kind of exponential model? Nothing was changing really qualitatively when you increased lambda. There's a difference between lambda bigger than 1 or lambda less than 1 then when things die off, but it's not more complicated than that. If you take the unimodal map, some other things could happen not very dangerous. Like if you look at this different value here, I just changed it a little bit. There is still some equilibrium point. There is a difference that it's going to be repelling this time. So if you're close to it, you don't tend to get closer to it. You tend to get far away to it. So that, but there appears here this little square. There is another value that after 1 unit of time doesn't stay the same. It changes. But after another unit of time, it comes back to the same state. So that if I was looking things every 2 units of time, things would not be changing. But it would depend if I'm looking at odd units of time or even units of time, but otherwise, nothing like this, nothing more. But so this, what happens in this picture is that this, what you call a periodic 2 equilibrium of period, an equilibrium of period 2, it is actually stable. It tends to attract nearby orbits. So it happens that if you start somewhere with few exceptions, you do this game of Marcelo, and it got closer to the red point, but then the red points expel the orbit towards the green points. And then what you actually see after a long time is basically oscillating between those green points. So that's the story that starts, and then you can try to play with these parameters. So this guy in 76, I think, a biologist that was interested in ecological and really populations called Robert May, he decided to write a paper describing what is the consequence of having a population that evolves according to this model. And he finds out that this is just the beginning of the story, and something much more complicated happens later. Extremely complicated, and this excited and brought attention to this kind of models. But in effect, he was just discovering things that had a significance that connects to much more of dynamical systems. So in this talk, I'm going to connect this with the beginnings of dynamical systems and see how actually these kind of models appear very natural and not only connected to this specific example or otherwise. So, so then you have to, like, I'll come back to these guys, but have to go to the beginning of the story of dynamical systems. That actually leads to this guy. So this is really the beginning. So that's with the people that I asked to try to guess who are the 4 people that are going to appear. So that's the first one. Then you so it really starts. So it really starts with Newton. So Newton, he made an important discovery that. He initiated the techniques to deal with differential equations, discovered that differential equations were useful to understand reality, and he started the things beginning with one of the most significant that he started studying was the ones of gravitation. So he got, well, he discovered that gravitation, the differential equations are important. It's the equation F equals ma. but this is the basic law. And then, but then you need to know what are the forces, and then he writes up the equation for the case of gravitational interaction. So you know that you have then the mass attract proportionally to so the points attract proportionally to the mass, and with inverse of the square. So there is some formula that I don't write, and this gives you the force. The force acts on how the system will move, and this will be described by a differential equation. And then what happens in the long term? So in practice, he was taking things back. So he knew the solutions because some people had kind of done the experiment, done the observations, astronomical observations. The people in the previous century were already measuring. They knew that things should there will be ellipses appearing and things like this. So he better also, if he wants to find the formulas, his formulas should give ellipses at some point. So he carefully found that. So then I embedded putting animations in my PDF file. This is what happens if you have some specific configuration of two, so you have two points, massive points that are interacting. It's not exactly very close to, let's say, Sun and Earth because they look a little bit similar. So one is not much more massive than the other and so on. So that's one picture that I found. And so they just do this thing, this elliptic movement, and he can write the formulas, Newton can write the formulas and describe those ellipses, and everything is very predictable. Like if you describe at the first, basically what's happening, the trajectory of the Earth around the Sun does something, then it's periodic, like after 1 year, you're basically at the same place, and nothing seems to be changing very much. So if you look a little bit more, there's a little bit of correction, but it is basically very predictable. So if you want to look at, say, what's going to happen in 1 million years, more or less, and you're just caring about those gravitational laws, it matters whether you are in the spring or you are in the fall, but otherwise it doesn't matter much more. So the 1 million years you ignore, and you care just about whether you are in which season you are. And otherwise, things didn't change. Even if you let 1 million years or 1 billion years, as long as you don't let other effects appear. So that's the easiest example. And then, very well, that's very good. But then it's remarked that, in fact, Earth and the Sun are not alone. There are other things. And you might be interested in see what's the consequence of having Jupiter around. If something will influence the behavior of the system, the guy that will influence first will be Jupiter because the biggest. So you could try to model the same things with 3. And maybe you can get a little bit more complicated equations, and you need to try to find out those equations and see that what complicated curves you would be doing and what kind of periodicity it would be happening, and how can you describe what happens after millions and millions of years. So one animation of this, it starts at some moment and then does something that looks more complicated. It's more complicated. Maybe you just need to kind of work hard and find some uglier equations, and eventually you're going to be understanding exactly what's going on. Or maybe this just looks ugly because I started with an ugly configuration. If I had started with, let's say, Earth and Sun, that they seem to be doing more or less just by themselves, and you just add Jupiter, maybe you get some equations that will be looking very much like ellipses, and you just need to kind of describe it, and then, what you're really interested would be to say what the kind of stability things that I said. Maybe you add a few corrections, and then, but the corrections be small, they don't, and you understand them very well, and this would be your goal. And but Newton didn't succeed. And then takes hundreds of years, and people are still trying to do that. And then we get to the stage where some new understanding is obtained. So people are trying to do what we call integrating this equation, find the right equations that, like you had for ellipses, more complicated and so on, that will lead to a description of your system. So people are trying to integrate the equations, and then arrives this guy. Next one. So this, everybody guessed it correctly. So that's Henri Poincaré. He decides to tackle the three-body problem. He has partially motivated, so there is interesting story around the partial motivations, that there is a prize given by the king of Sweden, Oscar, It was being administrated, I think, by Mittag Leffler, a very important mathematician, who was friends of Poincaré as well. Probably he was sure that Poincaré would get the prize. He would he needed to write a memoir, which would be very good, as always, and then there would be some incredible contribution to the three-body problem. That's what happens. He gets to describe very well some restricted version of the problem. He doesn't solve it completely, but he gets a big achievement. And then he gets a prize. And then there is something very annoying that happens that, unfortunately, he finds that there's a mistake. So he thought that he had contributed a lot to the understanding, to the stability and how to describe this three-body problem, and sees that actually he was wrong. He was not kind of managing to understand that well this, and then he had made a mistake. And he was a little bit ashamed, and then he used all the money of the prize to buy back the printing, because the prize was to get this for the best memoir that was going to be published in this journal called Acta Mathematica. And, but then he didn't want his mistake to be published, so he bought back, and then he spent all the money from this. He was quite annoyed. Everybody was annoyed at the situation, and then he kept kind of, he tried to understand better, and then he reached a great understanding, which he explained to Mittag Leffler, that probably was annoyed with him at that time. This I found in a book, so you can try to find this book. So this book is La correspondance entre Henri Poincaré et Gustav Mittag Leffler. I just found because I need the citation. So there is a discussion of this, and I got this page. And then he's saying that he's trying to understand what's actually happening. So things are not that simple. And he got into what was creating problems for him was that he found out that he was analyzing some kind of special kinds of orbits. They are related to this kind of equilibrium that we discussed before. So we saw in previous pictures two kinds of things that equilibrium could do. There was this equilibrium that was stable equilibrium that was attracting nearby conditions, and there was unstable equilibrium that was repelling the nearby conditions. There were the green points and the red points. But now we are in higher dimension. So this things for n-body problem is in higher dimension. So actually you're not fully attracting or fully repelling. Your equilibria, they actually might attract things along certain directions. So if you're near your point, you might be kind of attracted towards, and another ones you might be kind of expelled by it. So there are those equilibriums that are kind of, and the dynamics nearby then is a little bit more complicated, but not much more complicated than that. So that's kind of still easy to describe what's happening in the neighborhood of this equilibrium. But what happens that, let's say, an orbit that is expelled, so you could look at orbits that kind of whose future lies into my equilibrium, and there are other orbits that are coming from the equilibrium, so that the past comes from the equilibrium. But what can happen is that there are orbits that kind of may reach the equilibrium in the future and in the past. Those are not local orbits, but what happens is something further away. So they are doing something near the equilibrium, but then they go away, and they do something else somewhere else, and then they somehow connect and come back to the equilibrium. So those orbits that kind of have the same past and the same future are called homoclinic orbits. And he found out that those homoclinic orbits, they are very simple. They just kind of go to the past and to the future. They do the same. But nearby, something more complicated happened. And then he tried to make these drawings that us mathematicians we do, that like some of that I could be doing here, to see what would be the behavior of those of the guys nearby. And he says that he didn't manage to kind of get a nice picture. He says that he's describing here in French that it gets something very complicated, infinitely detailed, and they kind of don't kind of, they do something complicated, and then it's very complex, that it will impress you, it will impress us the complexity of this, and he will not attempt to draw. But it's so complex that he believes that it gives you a proper idea, and nothing else gives such a good idea that why this thing that you're trying to understand, the problem of the three-body problem, why is it so complicated? And actually, this shows why all problems in dynamics have some complication that's expressed by this picture that's not here. But it was something that was, besides discovering a phenomena, he had a remarkable intuition of the importance of what he had discovered. He was, the words that he used are extremely appropriate if you know the story of the subject. That's an important contribution, but to go on, you need to see there's another guy that comes in between, but I go along this frame of and the continuation of this with our friend that was also in Marcelo's talk, so Steve Smale. So Steve Smale, at some point, had proved the Poincaré conjecture in high dimensions and searched for a kind of challenge and decided to go to dynamics. And because there were a little bit of dynamics in the Poincaré conjecture, but very simple, and then he thought that, well, I proved the Poincaré conjecture, I can address any problem. And then he tried to address, to describe dynamics much better than everybody had done before. And he proposed that dynamics actually were pretty simple. He ignored Poincaré and those guys from before. He thought that everything would be simple and solvable. He was not actually concerning the same models that Poincaré was doing that are conservative. He was doing dissipative, but still it was a little bit ignorant. The point is that he learns that he's wrong. And then the big mark of all those people that make mistakes, but they're still great, is because they kind of don't give up from that, and then they do something even better than what they initially planned to do. What he did here was to make an important discovery that he describes this, and something that connects with my hometown. So he writes an article that's called "Finding a Horseshoe on the Beaches of Rio," that talks about his discovery that was made in Rio while he was visiting. He was interacting with Brazil at the time, partially because of another guy in that picture that was Mauricio Peixoto. So what is that he's finding this horseshoe? This is just kind of a nice thing that to show the connection to Brazil. But what is it that he found? What's this horseshoe? It's related to this phenomenon that he discovered. There is this complexity that arises from non-clinic points, and this complexity comes basically from something that's happening near this equilibrium that I said that there is this thing that things get attracted in one direction, so they're contracted in one direction, expanded in the other direction. So I represent here, I'm not saying the square to itself because I want to kind of show the evolution and it would get convoluted. But let's say in the first moment, because of this action, the local behavior there is something that was squarey and became this kind of rectangular thing by a contraction in one direction, expansion in another direction. But then there is something that happens elsewhere that does some folding. Takes this rectangle and makes it into that shape. But now I'm going to look at it in the same picture. And actually, so it takes the square and by moving this. So that's just a model of something that could happen when you plot something that was kind of contracting, expanding, and doing something else. And they do the simplest thing, you get this shape, and then it's obviously why it's called the horseshoe. And then once you have this shape, you try to understand what happens when you kind of repeat this process to itself, and then you get something that kind of folds like this. And this is just 2 iterates, and I don't kind of make the effort to make more iterates. It gets more and more detailed, this kind of oscillations and something like this. It was basically something like this with many oscillations that is what Poincaré would be scared of when trying to draw his picture. So he was saying likely things like this, so we don't see the thing. One thing that I put here is that there is some kind of complexity that's appearing here that is initially you had one square, but then it kind of folds like this. And then there's a left side and the right side that you can use. That's used for coding later. But once you iterate again, you get like 4 possibilities, like at least in some of the directions. You can get one to the left, left to right to the left, blah, blah, blah. You can code not with left and right, but with binary numbers. You get this kind of coding here. So that what I mean here is that after each time you iterate, you double the amount of information that you get in this direction. You get more possibilities to describe where you are. So there is some kind of exponential growth of complexity that will appear related to this picture. What Smale found was not only that this picture existed, and that leads to kind of these exponential complications. But also that though it's very complicated, it's remarkably stable. It is, after you kind of try to move a little bit this picture and change the exact formulas, you get something that looks remarkably similar. He discovered the possibility of structural stability of complex systems, which, as long as some conditions are met, so that is not going to happen always, but it can coexist some kind of very complicated behavior that's with some kind of stability. So that's a very important discovery that he made, which connects us with a famous object that was discovered in connection to meteorology. So there was around beginning of 60s, a meteorologist with mathematical formation called Lawrence tried to look at equations that describe the weather. It was too complicated. He looked at just a simplified version of those equations, so he eliminated many variables. He was left with 3 variables, and tried to plot what happens, and discovered that even when he simplified to the most, he still got something extremely complicated. So he got at this. So that's the iconic representation of the complications that you get when you try to understand anything about the weather, that even after enormous simplification, that's what you get. So just complicated. That looks like a butterfly. I don't know if that's, it's also connected to the butterfly effect, because when you talk about weather, we talk about the complications of this are related to this that I'm not going to describe immediately. But the point is that you have this evolution of orbits. So this is a differential equation that he's describing. I'm describing the orbits of the differential equations. Instead of having nice ellipses, you have this. And this is very complicated. It has, you could put some coding here as well, because there are 2 wings of the butterfly, the left and right, and you try to pay attention to whether I'm the left side, I'm in the right side, and if I'm flipping from left to right, and seeing what kind of sequence I get of how I'm switching from side to side, and see the whole things that get. And I get something very similar as what you get from the horseshoe, but not exactly the horseshoe. This is not exactly what Smale was doing, but it's very similar. It's not stable in the sense that Smale said, but it's essentially as stable as you could get in the situation. It's not a uniform hyperbolic system, but it's called a singular hyperbolic system. It's complicated like the horseshoe. It has stability, a lot of stability like the horseshoe. And on top of that, contrary to what it might look like at the first time, and that's the final point, is with dynamicists, we could reach a point and we say, well, things are complicated. Like even if you have not a lot of very complicated equations, what you get is extremely complicated, and so we can't use dynamics to do anything useful anyway. That's not the case. And the fact is that what is hopeless for systems like this is to do deterministic prediction. What doesn't make more sense anymore whenever we have this picture is to try to answer the question, what's going to be my state in 1 million years? That's not very likely. For weather, it doesn't make sense what's going to be the state in 1 month, exact state. Like, is it going to rain or not rain exactly in 30 days? Question cannot be answered, even if you have more and more spending on the meteorological opera and so on. Because it's too complicated, and things get more complicated exponentially fast. That's the sensitive depends to initial conditions. But not because you, and Marcelo emphasized at this point, it's not because you cannot do this that cannot say something useful. And that's where it comes, the idea of doing statistical description of the system. It's similar to the following issue. And because you have zeros and ones, and which could be called heads and tails, heads for left and tails to the right side. The question is, am I going to be the left side, or am I going to be in the right side after 1 million years? It's a question that you may ask, and I said that doesn't make sense, that I cannot answer. We are not going to be able to answer. But there are other questions that we would not be able to answer, and it would not surprise anybody. If I kind of threw a coin and asked, is it going to land heads or is it going to land tails, doesn't surprise anybody that I cannot say anything very meaningful with respect to this question. I can say that there is 50% chance that it will be heads and 50% chance that it will be tails. And this can be useful still. what it happens that while I cannot predict exactly one value that I do, if I can say very accurately that if I throw 1 million times and play this game 1 million times, I will have about half, and with very enormous likelihood, it should be close within certain range, I have about half of heads and half of tails, so about 500,000 of each. Well, with some fluctuations. And even those fluctuations you can describe. So there are things called the central limit theorem and so on that I'm certain everybody heard, that are very useful and allow you to say meaningful things about this. So the point is that statistical description is useful, and it can be applied to systems like this. This kind of system can be analyzed by this. By the way, this has been shown to really behave according to this. So this was kind of numerical work that kind of rigorously proves this by Warwick Tucker. But I'm telling about something that really behaves like this. And it admits a statistical description. We are able to say the kinds of things that I say that are interesting. Before moving on, I remark that, so here we have systems that are described as if they were random, but they are not random at all. They are deterministic. But the fact that they are chaotic allows you to describe them as if they were coming from the stochastic process or so on. It gives you, the chaos gives you a remarkable tool of analysis that sometimes is more powerful than what we would have for simple systems. So chaos can be helpful for you. Anyway, so that takes our stories, and now you are ready. After you learn all the story that lands us in 6, you can go back to the 70s and to our, if I'm not mistaken, to our picture. Yeah. So if you keep doing with this, and now you're looking at another parameter. So far, we had seen an equilibrium, we had seen a period 2 equilibrium, and so on. Already for this picture, you could kind of keep doing this. It did this, and here it's not seeming to settle into anything. Marcelo had a longer picture of this that also was seeming even less to be settling into anything. And it's because if you try to see the possibilities, and Robert saw this, and other people were interested in this around this, but I'm just emphasizing this point of the story. What we were seeing before, I think my parameters originally, so here I have, in the horizontal direction, I have the parameter space, the parameter variable, there was this R in front that was 2.7 in the beginning, and here's my dynamical variable, is what's the percentage of my body is filled with bacteria. It can go from 0 to 1. So, and initially we had 2.7 as my parameter, and there was a single equilibrium, so which represented in the vertical coordinate. So here, there was 2.7, and you see here that here I'm plotting where the orbs are going. And then there was a parameter that was 3.1 in the second picture. And then there are 2 points that are going to be crossed here that represents between those 2 points you're going to oscillate. You move from one point to the other. And now I have 3.8, and I'm in a region that's kind of much more, I'm not in this white region, a little bit to the left, and I'm kind of in a cloud of, a gray cloud of incomprehensible things at this scale. What the connection with this is that essentially you could see it arising from that, is that you had this horseshoe that came from this folding, but the folding was not interacting with anything. After it comes back. It was a harmless folding, the folding region. And then you got this kind of stable things that then can be very well described. The horseshoe can be very well described, and the Lorentz attractor can be very well described. This can be less well described. Well, it should be more complicated, but certainly doesn't have the stability of the systems that we discussed before. And that's because you don't fold as well, because the folding interacts with my expansion in a more complicated way. It comes back and hits itself, and the story is more complicated. And there are regions where things are fine, that the interaction eventually ceases to interact with itself, like here, and so on. And there are areas where it keeps interacting more and more complicated ways, and you get this gray cloud. So this whole story is connected to the progressions that we saw before. And as we saw before, we try to make a description that is in terms of statistics, if necessary. So basically, as was described by Marcelo, there is this remarkable theorem of Misha Lubitsch that says that fortunately you can describe a lot of this picture, 100% of the picture actually, that says that essentially everything that you see here, 100% of what you see, is either this kind of periodic behavior that can be described to the end and is kind of boring after some time, or it's complicated behavior, but of the good kind, the one that you can analyze statistically, the good chaos that you don't throw your hands and say, I'm not understanding this. I'm saying it's complicated, but I can tell you how is it complicated, which you see in this gray region. So that's the theorem of Misha in words. I hope that I'm not going to describe more about this because then I get to much more complicated things. Let me say that other beautiful fractals appear while you try to prove the theorem of Misha. The connection between a version of the bifurcation diagram that's written there. I flipped something, I changed a little bit the variables, but it's really the bifurcation diagram corresponds to features of this beautiful fractal that's called the Mandelbrot set that I'm sure that you have seen before, and then you get the right to see a video here that's just this is just an exploration of the Mandelbrot set, and it's for the purpose of this talk, you can imagine that just see that in dynamics you can get prettier and prettier pictures, and for another purpose of this talk, you see the kind of integration of mathematics that kind of exploring this kind of beautiful fractals, perhaps just because they are beautiful, and trying to say very specific things about those shapes and things like this, answer questions about the real systems that you described before. To tell as much as we know nowadays about that bifurcation diagram comes from understanding things that are very specific about these features, about the shapes of tiny bugs that appear here and things like this. So there is this kind of continuity of this. So anyway, like another copy of the Mandelbrot set. It is a connected subject, and in dynamics you are going to be able to deal with all those kind of nice things. Anyway, so that's, but I cannot explain what is about those kind of fractals that help, but they do. They appear in the proofs. So there is this thing. So that's kind of just, let's accept that. And then, okay, so that the quadratic family that we discussed is a success story in dynamical systems. But what happens to this thing that was started by Newton, like which was the discussion of the three-body problem and so on? Did we kind of eventually got better? There was progress after Poincaré. The most significant one was by our last guy, so congratulations to people that guessed it. That's Kolmogorov. And so in around 54 that he announced the thing, he discovered, he made the most significant contribution since Poincaré. So Poincaré had discovered that things were bound to be complicated, so it's inescapable that you're going to have this kind of complexity. Exponential complexity will arise somewhere. And he discovered, Kolmogorov, that there will be also, this may happen, but there will be a lot of stability also in some regimes, but this is not incoherent with having a lot of the part of the dynamical space that you can still, that is as regular essentially as it was in the two-body problem, as in the situations that Newton could describe. So when you had this kind of nice ellipse. It just gets a little distorted, but none of this exponential complexity will appear at some parts of your space. So that incredible discovery, I represent in, like I found this picture here. This picture is of some application in 2 dimensions that can be analyzed with the techniques of Kolmogorov and his fellows Arnold and Moser. That contains the spirit of a lot of the complications related to the three-body problem in low dimensions, relatively low dimension. What I'd like to see is that there are these kind of islands here with things that look a little bit like ellipse and so on. That's regions where you have regularity on your motion. You get pieces of regularity that survive the fact that the dynamics is complicated, and the complications of the dynamics are represented in this green area. So there's a green sea that's represented here that takes part of the picture. And what it represents, the region where it's unpredictable, it behaves chaotically as in the situations of the Lorentz map and so on. The difference of this picture is that nowadays we are able to justify, thanks to Kolmogorov, the existence of this kind of stable parts. But existence, so Poincaré and nearby and similar techniques are related to understand this horseshoe and so on, says that there are orbits that are more complicated, that are chaotic. But nobody can see that they form a C, that they are kind of visible in a picture. Maybe they exist, but they're not they don't affect very much the things. They just kind of, is some complications. But the fact that they can be seen with kind of high likelihood and so on is something that's completely so far out of reach. So that understanding that there is a green sea, in fact, mathematically provable in any variation of this picture that's not kind of specially designed to kind of have this feature that arises natural and so on, has never been, is one of the biggest challenges of dynamics. So that's the current state. I can say also that if you don't want to kind of be very sad about this, you can deal with some other use the ideas of Kolmogorov and the ideas of this kind of chaotic regions and so on to analyze other systems. And I was just going to end with a picture, but now Marcelo spoiled so he talked about this. He talked about this discussion about quantum mechanics and the Schrodinger operators and so on. It relates to dynamics, and the kind of dynamics that you get are kind of simplified, very simplified versions of this. But where the chaos and the stable regions, they are more isolated, so they don't interact directly with each other. But you can transition from one to the other, and this is somewhat complicated, but not nearly as this picture. So it's a baby version that can be analyzed. So that's what gets to understand the picture that Marcelo showed, that I show another version. We didn't kind of plan together the talk, so that's another a version, like colored version of the picture that was drawn by Marcelo. So that's also the Hofstadter butterfly in a colorful version, and related to this model that's related to quantum Hall effect and so on. But this picture represents what it is really, is in a particular model, represents what happens is the phase transition between the stable region, the one where the dynamics is stable, so that was the small couplings that were described by Marcelo, that's a minimal to KAM, to Kolmogorov approach, and the other one that would be chaotic, where you have this kind of hyperbolic phenomenon. And this is exactly the representation, the fractal representation of what happens at the phase transition. And, well, I was not going to say those words, but since Marcelo said, this picture with its self-similarity and so on is again an example that at the phase, this picture is also not understood at the level that I'm discussing here, that at a phase transition, there is renormalization happening. And how do you know that there is renormalization happening? Well, just look at the picture. It's clearly self-similar. There is some operator. This is a parameter space. There is some operator that's not been described very well so far that acts on this picture and explains why it has some kind of, it looks like it does with self-similarity and so on. But anyway, the techniques that I discussed there, they apply to the Schrodinger operators, and other techniques like renormalization apply to other parts of the parameter space connecting everything. So, well, I hope I gave an idea of what us dynamicists are interested in and what's the story about that, and thank you.
Thank you, Arthur, and thank you also, Marcelo. That was a real treat. I hope everyone appreciated how they took very deep and important mathematics and tried to express it in a non-technical language. Some of it we understood, perhaps. Some of it we might not have understood. But I hope that regardless, you go away with an idea of how profound and beautiful this work is. I actually hope you also go away with something else, which was in Marcelo's talk. I hope this number registered on your mind. 18 million students participate in the Brazilian Math Olympiad. That's about half the population of Canada. So we've got a bit of work to do here. So I want to thank all of the speakers this evening for the insights that you shared with us, for the mosaic of ideas. Let me state something which should be obvious. Events like this are possible only because they don't just happen. They're only possible because of the continued and dedicated efforts of a large number of people, in this case, the Fields Institute staff, a large number that I can't name individually, but maybe I want to just single out Brian Eilhart here and his team. Let's give them all a round of applause. So I leave you now tonight with an observation that I made at the beginning of this evening, that as broad and as intense as the activity at Fields are, sometimes I do hear people speak of the Institute as a well-kept secret. I asked you at the beginning to help me change that. And indeed, I'll ask you again, if you like what we're doing and if you believe in what we're capable of doing and what the Fields Institute is contributing, then I encourage you to share your thoughts and your experience here tonight through whatever medium you're comfortable with. You can tag Fields Institute on various social media that you use. Now I'd like you to join us for a reception just outside the theater, where you can chat informally with each other and perhaps with also the speakers who presented this evening. Thank you and good night.